Okay, so today we're going to talk a little bit about Hammer. We won't be going into great detail on how to enter various properties of elements like hydropneumatic tanks. So instead, we're going to focus on two main things. First one being a few tips for taking an existing water model and setting it up for a transient analysis. And the second would be some key tools to help you quickly and efficiently analyze and understand your transient results and the effectiveness of different strategies. So just to cover some basics, some of you have already used Hammer, so you're already familiar with it. But just to recap here, so Hammer is our software for predicting hydraulic transients. It uses the method of characteristics, which is pretty much the industry standard, very robust, very stable. The great thing about Hammer, if you're a WaterCAD or a WaterGEMS user and you already have a model in either of those products, you can simply open that model right up in Bentley Hammer. You don't have to go through any import or export procedure. You just open up the model and you have everything you need to proceed with the transient simulation. And you have the same look and feel of the user interface. It looks very much similar to WaterCAD or WaterGEMS. So that can help you save a lot of time. So if you've only used WaterCAD or WaterGEMS before and you have to do transient analysis, this is a really great tool. So there's a lot of different things you can do in Hammer. You can model things like pump shutdown, startup, closing valves, opening valves, turbine fluctuations, lots of different transient protection elements that can be modeled, hydropneumatic tanks, surge tanks, air valves, surge relief valves, so a lot of different things that you can model there. Again, we won't go into great detail on all of those things in this meeting. So some basic transient theory. So what is a transient? Transient is when you're transitioning from one steady state to another. So if you're starting with a pump being on and that pump is shutting off, if you run that in WaterGEMS and you look at an extended period simulation, you're just going to see, okay, the pump is on, and then the next time step, the pump is off. So those are actually two steady state conditions. So in reality, when you have a transition between those steady state periods, there's some fluctuations that can happen, and sometimes they can be harmful. So what causes a harmful transient? Well, it's anytime you have a rapid change in momentum compared to something called a characteristic time, which is equal to 2 times the length of your system divided by the wave speed. So it's how long a wave takes to get from one end of the system back. So things like starting up your pumps too quickly, shifting their operating points, shutting them down too quickly, opening and closing valves or hydrants too quickly. If those things happen too fast, it can cause a transition to the new steady state that happens too quickly and can cause some pretty severe changes in hydraulic grades, some severe pressures, both positive and negative. So there is a standard formula called the Joukowsky equation that you can use to kind of do a quick approximation of the actual magnitude of that hydraulic grade change or head change as a result of a change in momentum that's less than the characteristic time. That's really just a rule of thumb. It doesn't account for a lot of different complexities that Hammer can account for. So some of the risks for hydraulic transient, obviously it can damage the pipes if it exceeds the rating of the pipe. It can actually move structures just from the forces that act upon the pipes from a transient. You can actually damage your pump house or anchors and things like that. If you have problems with low pressure surges, you can actually suck in contaminants into the seams of the pipes, and that can cause some issues there. Also, if you have air or vapor being introduced into the system as a result of a transient, that can actually cause some blockages and reduce the performance of the system. Okay, so some basic workflow for Hammer. Basically, you prepare your model. Usually it's best to simplify it. We'll talk about that a little bit more. Then you enter all the transient-specific properties of your elements and any configuration that's Hammer-specific. There's a few things we'll cover on that. Then you want to set up your scenarios for the various events that you may want to model in Hammer. Next step is to establish those initial conditions. So remember, we're starting with an initial steady state. We're transitioning to a new one. So Hammer has the ability to take advantage of the WaterCAD/WaterGEMS hydraulic solver to basically calculate a steady state for you to establish those starting initial conditions. Then your next step is to compute a transient simulation, which takes that initial starting condition and sees what happens when you transition to that new steady state, pump shutting down, valve closing, so forth. Lots of tools for viewing and understanding the results, and that's a key area that we're going to touch on. Make sure you're nice and efficient with understanding those results. Last thing you usually want to do is a sensitivity analysis, where if you're not quite sure about a certain setting of something, or if you're not sure what size of a tank or size of an air valve you might want to use, you can basically vary those parameters and check the transient response to that to see if it has a significant impact on that, so if it's something that you need to really refine. Okay, so what do you need to do to prepare the model? So if you have a WaterCat or a WaterGEMS model, first thing is you want to make sure that it's in really good, stable conditions. So, make sure it's calibrated. You don't have any issues with the model being unbalanced, or, any issues like that. Hammer is a little more sensitive to those kind of things that you can sometimes get away with WaterGEMS model. So you want to make sure that your initial conditions are nice and accurate. Then consider, what kind of conditions will you be using as that starting steady state period? Will it be at a time when you're experiencing your peak hour demand, your average day? Should I start it with the tanks at a low level, a high level? So it's something to consider. Next thing you want to do is, if at all possible, simplify the model network. So if you have a really big model, maybe a city or subdivision, one option is to just use the model as is, but it's highly recommended that you skeletonize the model, which is to say, simplify it down, remove model elements that may not really experience bad transients, and kind of focus in on the area that you expect to see the worst effect of the transient. But you do want to stay connected to any significant boundary conditions. So if you have a pump station that's pumping up to a tank somewhere downstream in the system, you may want to skeletonize it from the pump out to that tank. Another method is to basically cut off the model at a certain point and insert either a demand or a reservoir to sort of assume a boundary condition. We'll